Now we will see the result for turbulent flow over heated cylinder. So if you go here in the problem statement, we have to find the contour for velocity, temperature and pressure. We have to plot the velocity, temperature and pressure at different downstream location. We have to find the surface heat transfer coefficient, average Nusselt number and total heat transfer. So we will do that. First of all, the contour. So go to graphics and animation, go to contour, setup. So we already have created the plane during the laminar flow problem. So this is the plane. If you want to see the planes, everything, go to mesh, setup and select all of these, display. Right now this is your domain. Select plane 1. This is the plane at the middle, so mid plane. So we will plot our velocity, temperature and pressure contour in this mid plane. So go to contour, select velocity, velocity magnitude, plane 1, display. Go to here, make it normal. So this is the velocity contour at the mid plane, as you can see here. If you go to the problem where we saved the velocity for laminar flow, here you can see this. So we have the flow contour for laminar flow, the velocity magnitude contour, and for turbulent flow this looks like this. So in the whole domain you have a very high flow rate, and just at the downstream of the cylinder you have a very low flow rate. For turbulent flow, it's expected that you will see lot of vortices and lot of eddies, but as we are doing K epsilon model, which is a very normalized, very simple Reynolds average Navier-Stokes model, so it average everything. So that's why you will not see the vortices at the downstream of the cylinder. If we do LES, then you will see the vortices and the eddies at the downstream of the cylinder. So you can save this picture. Where you saved your laminar flow problem. Here you save it, velocity. Save it. You can also see the pressure contour. Save it. Turbulent pressure. You can also see the temperature. So this is the temperature contour. Here you can see for laminar flow, when we have the laminar flow, here we have the temperature contour. Here you can see the downstream location, the temperature of the air increases at a longer range because it had lot of time to heat up this downstream air, as the flow velocity is very low. But here at turbulent flow, the free stream velocity is very high, so the outside air at the downstream of the cylinder does not get too much time to heat up. That's why it didn't heat up that much. You can see the temperature contour, everything around the cylinder. There is a little zone where you can see the temperature is increasing, otherwise the temperature is inlet temperature. So this is the difference between laminar and turbulent flow. But in the case of heat transfer and heat transfer coefficient, you will see the change. So save this also. Turbulent temperature. So we saw the temperature, pressure and velocity contour. Now we will see the plot. So go here, plot option, and XY plot, go here. So we want to see the change of velocity, temperature and pressure at the downstream location. So if you are not sure at which line we want to see, you can always go back here and you will see which line. Select line 1, this is at the downstream, first D, line 2 and line 3. So we will, and this is line 4. The velocity, temperature and pressure at line 1, 2 and 3. So go to plot, XY plot, velocity magnitude at line 1, direction vector is at Y. So plot, here you can see the velocity. So this is the velocity at line 1. As you can see, the velocity magnitude, it reduces just behind the downstream of the cylinder and then go up again and increase. At line 2 it changes, line 3 it changes. So you can see very specific change of velocity at different downstream location. If you want to save this, you can save this here. So if you go here and if you see the previous velocity, this is the laminar velocity, and here this is the turbulent velocity. So you can see the difference between laminar and turbulent flow here. Same thing happens for temperature and pressure. Let's say we want to draw the temperature. So go to temperature, static temperature, plot. So this is the temperature distribution. For 1D, this is here. You have maximum increase of the temperature is 305 degree Kelvin for line 2 and for line 3 here. So you can see the temperature at the downstream location. If you want to save this, you can save this here, and if you want to see your temperature, here is the temperature when we did the laminar flow problem, and here is the temperature distribution when we are doing turbulent flow problem. So you can see the difference. Now we saw the line plot and the contour. Now we want to see the surface heat transfer coefficient, average Nusselt number and total heat transfer. So in the laminar flow problem, we saw the Nusselt number was 5.15 based on this calculation, and we found our age 2.45 and our simulation was 2.13 and the heat transfer was 5.15 watt. And here we will see when the flow become turbulent what will be the heat transfer. So go to flux, setup, total heat transfer, cylinder wall, compute. Then you will see here the net heat transfer is right now 159.57 watt. So the heat transfer increased a lot due to high velocity. That makes sense because when you have a turbulent flow, your heat transfer coefficient will also increase. We will see that also. So if you go to surface integral and if you select area weighted average, wall flux, surface heat transfer coefficient, select cylinder wall and compute, you will see here our heat transfer coefficient is 71.79. Here for laminar flow we had H 2.45. Right now for turbulent flow we have the heat transfer coefficient is 71.79. So the heat transfer coefficient increases with the Reynolds number, that is when the flow become turbulent, your heat transfer rate and your heat transfer coefficient also increases. So these are the overall findings and difference between laminar and turbulent flow over a heated cylinder. You can do lot of calculation based on this. You can compare the laminar and turbulent flow. You can use different turbulent model. You can see the change of heat transfer and heat transfer coefficient and the flow field when you use different turbulent model. You can practice those things, you can change those things, and you can play with this turbulent model and you can see which model best suits your problem. Based on that, you can do lots of interesting things in Fluent. You can also model complex problem by large eddy simulation, and you can also see the difference between Reynolds average model and large eddy simulation model. In the next tutorial we will see some internal flow, that is flow through a pipe, and we will see different parameters for laminar and turbulent flow. Thank you.